Yongjin from Panmnesia, and I'll present our recent work titled A Silicon-Proven Unified Low-Latency CXL Controller and Port-Based Routing Switch for Memory-Centric Fabless. Long title. Let's see. This is the motivation, and I would assume that everyone understands what I'm trying to say. So with the advancement of the AI applications, the memory demand is skyrocketing nowadays, and so the price. So to solve this issue, recently people have been talking and thinking about expanding memory using memory-centric interconnect technologies such as CXL. So the CXL firstly released in 2019, and after its first release, there have been some prevailing views. And today I'm going to talk about the scalability of the CXL. So let's take a look at the CXL scalability. So we have single-headed device, multi-headed device, and a switch-based scalable system. So if you think of in terms of scalability, it's important to have switches in the middle. But there have been perception that if you connect switches in the middle, the latency performance goes beyond some practicality. So that's actually one of the issues that people find so far. And there have been some studies about the latency performance of CXL. As you can see from the table, the latency, even without a single switch, is about from 250 nanoseconds to 450 nanoseconds. So if you think of connecting switch in the middle, as you have more depth in the middle, then you can expect that the latency increases proportionally to the hierarchy of the switch. And we looked at the issue closely, and I found that this behavior stems from the characteristics of early stage CXL. So by early stage CXL, I mean the design or the structure of a CXL controller that borrowed a lot from the PCI Express structure. Because CXL and PCI Express shares there's some commonality, right? They share the physical layer. But the early design ended up borrowing a lot from the PCI Express design. So for example, PCI Express has to process variable length I/O, and actually it has the serialized data path in between layers that actually incurs high latency. And latency is not the only issue with early stage CXL switches. We need to think something in terms of memory sharing. The diagram on the screen shows the switch-based architecture, which is called HBR, hierarchy-based routing. Because this HBR, all devices attached to switches are confined to a single host domain. So as a result, if you'd like to implement a cache coherence, you need another additional support by software. So here, I'd like to raise a question for you. So do you think these limitations that I provided just before are inherent to CXL technology or CXL switch? So what do you think? Any thoughts on that? So, whenever a presenter asks a question, the answer is quite obvious, right? So our answer is no. And we actually believe that this actually stems from the PCIe-driven characteristics of early stage CXL. So once we have next stage CXL solutions characterized by optimized transaction processing, memory sharing support, PBR support, and support for CXL Gen 3 or later specifications, then these issues will be gone. So with next stage CXL controller or next stage CXL solutions, we can actually have way better scalability, and the latency performance will become comparable to those by single-headed devices or multi-headed devices. So now let's look at the solution based on the next stage CXL. So the next stage CXL, it is composed of two different modules. One is a basic controller, CXL controller, and the other is additional module for routing. So first, let's look at the inside of the CXL controller. So as you can see from the screen, the internal architecture is different. Because CXL has a fixed length plate, we can combine the layers in a single clock domain, and then we can also maintain shared buffer to remove the interlayer synchronization overhead. another optimizing we can do is at each level. So at the transaction layer, we apply the traffic-aware message scheduling. As you may know already, the CXL has 3 different protocols, which is CXL.io, .memory, .cache. Depending on the traffic pattern of these different protocols, we can manage the traffic efficiently. And at the data link layer, we apply latency optimized FLIC, and as a last, like a physical coding sub layer, we employ nominal empty elastic buffer design instead of nominal half-full design. So with all these optimization techniques, we could reduce the latency of the controller significantly. Now let's look at the routing part. This is about the second module. So this routing module supports something called PBR, which stands for port-based routing. So every device is attached to port in a global fabric. And the traffic, all traffic is routed based on the port ID. And it actually can provide the efficient routing of the traffic. So here the global fabric refers to the structure formed by interconnection of CXL switches. So because a global fabric allows connection of multiple hosts, devices are not confined to a single host domain anymore. And as a result, you can have the cache coherence natively with the PBR support. And this is another advantage of PBR. So as you can see from the diagram, you can have very good flexibility in terms of topology. You can have closed, torus, and mesh, depending on given your system requirements. And another benefit of this PBR is the system stability. So as you can see, even though one switch actually is down because of congestion or some other issues, you can still maintain the system operation. And this is about one characteristic of early stage CXL. Unfortunately, it does not allow inter-switch connection, so the scalability is actually limited because of the factor. And because PBR supports inter-switch connection, you can have a lot better scalability than the early stage ones. Now let's look at the routing module. So because we implemented a routing module in hardware such that we can keep the latency performance deterministic or low at the same time. Now let's go to the implementation evaluation. So we made a switch silicon that has the characteristics of the next stage CXL that I previously explained. And this PBR switch, the controller and the routing module are placed at each port, and a number of ports are grouped to form a port bank. And each port bank is connected through a non-blocking NOC as in the figure. And here on the screen, it shows the layout of the actual silicon. So we measure the round-trip latency and timing parameters directly from the silicon, and the measurements are applied to an RTL-based emulator for evaluation. And the figure on the screen shows the evaluation configuration. We have direct attached configuration and switch attached. And single-headed device, multi-headed device, they are based upon the early-stage CXL controllers. And switch basic is refers to a configuration that has legacy HEBR switch along with the early-stage CXL controller. And switch advanced actually has a proposed PBR switch with early-stage controller. And switch optimized is a combination of proposed PBR switch and proposed CXL controller. And I have more details on the table. If anyone has more interest, you may refer to the paper. And this is memory access latency performance. And the baseline is direct attached devices. So first one is about the switch basic. So with the switch basic, the latency increases about 280% compared to the baseline. And with the switch advanced, from 280%, it reduced by 35%. And if you have a switch optimized configuration, the latency drop becomes about 52%. So we can achieve about 2 times better latency performance compared to the early stage switches. And another thing is that the latency performance, as you may see from the graph, becomes kind of comparable to the latency performance of direct attach devices. The next one is the system throughput. So the baseline here is the single-headed device. So the multi-headed device, even though it's got multiple hubs attached to a single device, it does not give a lot of gains in terms of throughput. But however, the switch configurations gives a lot better throughput because it's got multiple ports out of the switch. And with the proposed switches, so switch advanced and switch optimized gives a bit more improvement in terms of throughput from the switch basic, and then this gain actually comes from the latency improvement that was reported in the previous result. The next one is about scalability. So multi-headed device and switch basic are more or less limited in terms of scalability. But as you can see from the chart, the switch advanced and switch optimized can connect up to 64 nodes, and the throughput actually almost linearly increasing along with the number of nodes. Okay, here's the summary. So by employing unified CXL controller and hardware automation, we could achieve very low latency of CXL switch and CXL controller. And then with the PBR support, we could achieve very good scalability performance as well. So if you're interested, please contact us for more information and for the project. Thank you for your time.